Alright, what's up guys? In this video we're going to pick up with some multivariable calculus, and we're back on the topic of iterated double integrals. So we're asked to evaluate this iterated integral here. It's going to be a double integral from 0 to 1, from 0 to pi. We got y squared cosine of xy dx dy. So what an iterated integral is basically an integral that's already set up for us, and we just have to just deal with it, evaluate it. And as I've said in the past, evaluating double and triple integrals actually isn't as bad as people may think it is. Oftentimes setting up these integrals is actually the hardest part, because a lot of times you'll need a sketch of the region, and that's even more so with the triple integrals. But very rarely will you be applying a whole bunch of integration techniques for double integrals and even triple integrals. It's typically not going, the integration is not going to be that bad, at least in a bunch of the examples that I've done. I've never really gone the entire integral using a bunch of techniques. Oftentimes just very simple, and it's even more so for the triples as well. I've actually done more work evaluating one integral than most double and triples. So, all right, so the first thing that we're going to do is we're going to integrate with respect to x. And remember how we do this. We work our way from the innermost integral to the outermost one. So what I've done is I go ahead and set up our first integral that we're going to deal with. And I always, even though I know we're integrating with respect to x and the y squared can be pulled out, I always kind of set it up this way just to kind of give you a general idea of how you need to start these types of problems. Now we'll go ahead and pull out the y squared, because we're treating that as a constant since we're integrating with respect to x. So this will be from 0 to pi, and then we'll have cosine of xy integrated with respect to x. Now hopefully you know how to integrate that, but if you don't, I'll show you how. All you do is a u substitution. You'll pick u to be xy, du will be y dx, and then you'll have 1 over y du is equal to dx. And again, as you can see here, we're running into an occasional substitution within a double and triple integrals, but again, you won't be applying a whole bunch of techniques to these types of integrals. It's not going to be that bad in most cases. You're probably more likely to run into more work for double integrals than triple integrals, but like I said, even when you run into some substitutions here or there, they're relatively straightforward. Okay, so now after we've done the substitution, I'm gonna simplify the outside in just a bit, but we'll need to change the limits of integration again. So u was xy. So to change the limits, I just substitute in for x, I substitute in 0, and then I substitute in pi, and those will be the new limits in this particular case. So it'll be from 0 to pi y. Then we integrate it. So y squared times 1 over y just cancels out one of the y's, so this leaves us with y. The antiderivative of cosine of u is positive sine of u. And now we need to evaluate it from 0 to pi y. And so what we'll end up with is y multiplied by sine of pi y when we plug everything in. And that's what we'll get. Obviously substituting in 0 just gives us 0. And so now we're down to our second integral now, from 0 to 1, and we got y sine of pi y, and this time we're integrating with respect to y. Okay. Now if you look where we got here when we got down to our second one, it looks very similar to the first one, but not exactly similar. And if you see, what happened was, well, I mean, the trig function did change, but it just dropped the power of the y down to 1. And so now we need to evaluate this one. And in this particular circumstance, this would be a good time for integration by parts, but it's a relatively simple integration by parts to do here. So integration by parts, that's the integral of u dv is equal to uv minus the integral of v du. we need a u and a dv. So again, this isn't hard. We'll pick u to be y, and dv is everything else. So dv is sine of pi y dy. So that means that du is dy, and v is the antiderivative of dv. So that's the antiderivative of sine of pi y with respect to y. Okay. And we know that that's just negative 1 over pi cosine and then pi y. So we go set everything up. So I'm going to move the negative to the front. So this will be negative 1 over pi multiplied by y cosine of pi y. And two negatives are going to make a positive. So this will be plus 1 over pi. And then we'll simply integrate cosine of pi y again. And again, that's integrating with respect to y, evaluated from 0 to 1. All right, believe it or not, we're almost done. Let's just get another sheet here. Okay, so we need to once again just integrate, and we already know what the antiderivative is because we computed it up there earlier. We computed one that was very similar to it, but so now we got cosine of pi y with respect to y. We need to integrate that now, and again that's just 1 over pi sine of pi y. Now since I already have a pi, a 1 over pi on the outside, and it's going to stay positive. 1 over pi times 1 over pi is 1 over pi squared. So we didn't do anything to the left-hand side, which was negative 1 over pi y cosine of pi y. And then this will be plus 1 over pi square sine of pi y. This will be from 0 to 1. So you just substitute everything in and see what happens. Okay, so if we plug the 1 in, look like we're going to get 1 over pi if we stick the 1 in. When we stick the 0 in, we're going to get 0. So this would be 1 over pi minus 0, which is 1 over pi. And yes, cosine of 0 is 1, but don't forget about the fact that we're substituting in the y. So multiplying 1 by 0 gives us 0. So we get 0 if we plug in 0 for y. And sine of 0 is 0. Okay, so that's how we know that that's correct. So the answer is actually 1 over pi. So the final answer for this double iterated integral, which was from 0 to 1, from 0 to pi, and it was y squared cosine of xy dx dy. The answer is just going to be 1 over pi. All right, so I hope that made sense. Again, relatively straightforward example. We've certainly done ones that are far more difficult than that, but like I said, you can always reach out and ask me questions at any time about anything. I'll be happy to talk about it. All right, so that's going to be the answer. So I'll see you guys next time.